concrete form design 1. We have two learning objectives. We determine the design load for wall and column forms, and then we also determine the design load for floor and roof slab form. So basically, there are two types of the forms we're talking about. For wall and column, it will be the vertical form. Then the floor and slab form, then it will be horizontal form. And the load work, the way the load apply, it will be different, as you will see in today's class. And then we design the slab forms, and then we move to the next week when we learn design the wall forms, and then use table to design slab and wall forms. So let's go to the first few slides that you have here. So this is the vertical format, you can see that. So when you place the concrete when it fresh look like a fluid, and it will have the horizontal pressure on the form. And if we are not set up the formwork correctly, it will be fall out, collapse, and the whole formwork will spill over, and that it will be disaster. And same as apply that concept if we set up for the wall or for the column. So the equation that I'm going to present in this lesson video apply for the vertical formwork, as you can show here, or the vertical formwork for the wall and for the columns. So how can we determine the load of the formwork on these vertical forms? That go to the note that we have in today's lesson. So concrete pressure, as I mentioned, concrete when it fresh is like a fluid. It have the horizontal load pressure on the surface its contact, in this case the formwork. So how to determine that? We use the ACI 347. So that is the American Concrete Institute standard for standard 347. We can be able to determine the pressure due to the concrete on the vertical wall. It means the columns and walls. How? So there are a few equations involved, depends on the scenarios. First equation that you see in here, P max equal to CW CC times 150 plus 9,000 R over T, and the equation here get the unit in power per square foot of the wall. That apply for all columns. So regardless of the rate of placement, regardless of the height of the columns, for all columns we will use this equation. But for walls, there are different scenarios. This equation can apply for the walls with the rate of placement 7 feet per hour. You know what is the rate of placement? Go back to the previous lesson when we learned the concrete construction. You determine the rate of the concrete placement, how many feet per hour the concrete will be placed. And as you can see that rate, if you increase the rate, it means you place concrete very fast. It will create more pressure on the wall due to the concrete pressure. So that's why it will depend on the rate of placement. And it measured by how many feet per hour, or in SI, how many meter per hour. And then what is the height of the structure, and that apply for the walls. So if the walls have the rate of placement, in this case less than 7 feet per hour, it means slow rate of placement, and then the height is not too high, less than 14 feet, then we can apply this equation. And of course all column, this will apply the same equation. CW, that is the unit weight coefficient, use table 13.1. CC, C stands for chemistry coefficient, depends on you use retarder or not retarder additive in the concrete that you learn in the civil engineering material, that table 13.2. And then the lateral pressure, power per square feet, that's what we learn in here. And then they get P max at some point. And then we have the rate of vertical placement of concrete, feet per hours. Concrete temperature, it depends on the temperature. If it's hotter, it tends to make the concrete harden faster, and that reduce the pressure on the wall. And that way you can see in the in proportional to the temperature for the pressure, as you can see there. And then the h is the height of the form. So height of the wall, how to set up that. Unit weight of the concrete, how heavy the concrete is. So it light, then the pressure will be light. It heavier, it will be more. So how to determine the CW and CC, and then we use that table here, and that's shown in the next few tables that you can see there in the slide. So this one, as you can see, if the lightweight concrete less than 140 pound per cubic feet, the CW will determine in this equation, but at least 0.8, at least 0.8. From that equation, if like 0.7, then you choose 0.8. And same we apply for the SI unit. And then if it somewhere the unit weight 140 to 150 pound per cubic feet, the CW is 1. And then if it over, so it heavy concrete over 150, then it divide the CW, what is the actual unit weight, divided by 147. For the CC, the chemistry coefficient. So it depends on the type of cement, so because related to chemical, and the additive, in this case retarder. Without retarder, 1. With retarder, 1.2. And there are other scenario that you can have there. So that be able to determine the concrete pressure on the vertical form. And this, it will be vertical applied to the vertical form. And the other scenarios that we're going to discuss. But before that, Pmax, it need to be at least 600 CW. What is CW? That is unit weight coefficient, table 31. And it cannot exceed that equation after you determine Pmax. Cannot exceed the maximum pressure, WH. I think WH is familiar with you when you study fluid mechanics, the water, for example. Then at the height, H, the pressure of the water on the surface, vertical surface, it will be WH. In that case, W is the unit weight of the water. But in this scenario, that is the unit weight of the concrete. So what does that mean? Pmax in that equation cannot be exceed WH, because the concrete before strand is fluid, but it's not 100% fluid. It's semi-fluid. So it should not be get that maximum pressure WH. At most, totally fluid, then it WH. So that whatever equation you determine, it have to be less than WH, and the minimum 600 CW. And that is apply for that equation apply for all columns and go with the rate less than 7 feet per hour and the height less than 14 feet per hour. What happened for the walls that had the rate of placement is more than 7 feet per hour and different height? That go to the next equation. For walls with the rate between 7 to 15, so it means that the rate of placement is faster. And the walls with rate slower, 7 feet per hour, but the height is more than 14 feet. So there are two scenarios for the walls that can apply to the second equation in there. Pmax equal to CW, CC, and with that equation there. And it's still that Pmax you determine, it have to be within minimum pressure and maximum pressure, 600 CW for minimum pressure and WH for maximum pressure have to be applied. So it cannot exceed the maximum pressure WH. And for the walls greater than 15 feet per hour, or when the form will be filled before the concrete stiffens, so that is not fresh there, then at most, as you can see, the Pmax equal to WH. So that is the pressure for concrete created on the vertical wall form. And again, this equation apply for the columns and for the walls only, not slab, not the beams. Go back to the final exam reference, that is item 5 that you have here, and we have different equations to determine the concrete pressure and apply for the goal and forms. And we have a table 13.1 to determine CW, 13.2 to determine the CC chemistry coefficients, and to be able to apply that. So let's move that so that you can use the equation to move to the next lesson videos. We learn to determine this for different scenarios in problem 1 and